This integral type was asked in 1999, and it's a particular type which involves a substitution, and the substitution is as follows. It's let x equal to 2 sine theta. Now just to explain where this comes from. 2 comes from the 4. 2 squared is 4, so whatever the root of this number here is, we use that. So if that was 16, for example, we'd use 4 over here. And the step you wouldn't think of is sine theta, because there is no mention of theta in the question. So you'd have to memorize that, or else they'd often give you that as a hint in the exam. Okay, so let's work with this side for a while, and let's substitution dx d theta with respect to theta, because theta is what's on the right hand side, so be careful there, equals 2 differentiate sine, and we get cos. And this gives us dx is equal to 2 cos theta d theta. Also, as we're at it, we can change the limits, because these limits here are attached to the x. So if x has changed, if we're doing things in terms of theta, we must also do the limits in terms of theta. So if we do the limits next, and first limit is root 3, so I'll put that in for x. So x is equal to 2 sine theta. X is root 3, so root 3 is equal to 2 sine theta. And therefore sine theta is equal to root 3 over 2, which means if you look at the tables, the angle which gives you a sine of root 3 over 2 is 60, which is pi over 3. So theta, be careful to do this in radians as well, because we're getting the inverse sine of root 3 over 2, and inverse sine is only defined in radians. So theta is equal to 60 degrees, which is pi over 3. Now do the same for the other limit, which is 0. That's a bit easier, because 0 equals 2 sine theta. Sine theta is therefore 0, which means the bottom limit stays at 0, because the sine of 0 is 0. Now we can return to the original integral, and we can just substitute in. So we get the integral between 0 and, instead of root 3, we now have pi over 3. Of the root of 4 minus x squared, and for x we put in 2 sine theta. That's our original substitution up here. And for dx we put in this here, which is 2 cos theta d theta. And maybe I just put a little line between these to keep them separate. Now let's work with this. We've got the integral between 0 and pi over 3 of the root of, let's just do that again, 4 minus 4 squared, empty in the brackets, 4 sine squared theta. And we still have 2 cos theta d theta, and that becomes the integral between 0 and pi over 3 of the root, take out the 4, 1 minus sine squared by again 2 cos theta d theta. So let's come up here. This is now the integral between 0 pi over 3. 1 minus sine squared is actually, you just put that in red, that's actually cos squared. That's the form of the tables. Cos squared plus sine squared is 1. So cos squared is 1 minus sine squared. Therefore it becomes the root of 4, which is of course 2 squared. I'm putting it as a square because it's going to cancel with the root in a minute. It's 2 squared cos squared theta by 2 cos theta d theta. Which is the integral of square root of 2, so we get square root of everything under the root, which is 2 cos theta. And we still have another 2 cos theta out here. D theta. And the 2 by 2 is 4, that can come outside the integral as a constant, so it's 4 times the integral between 0 and pi over 3 of cos squared theta d theta. And now we're back to a formula that's in the tables. And so when you come across this in an integration question, whenever you come across cos squared or sine squared, as we call the even powers of cos and sine, you have to use a formula from the tables, and the formula is the following: 4 integral between 0 and pi over 3. It's a half into 1 plus cos 2 theta d theta.